Welcome to Elektor Engineering Insights, the show that puts your engineering challenges to the industry's experts. I'm your host, Stuart Cording. If we are to become a greener society, it is not just enough to rip fossil fuels out of our daily lives. The electrical alternatives that will replace them need to deliver the highest possible efficiencies too. As a result, those involved in power conversion technology are continuously looking for ways to attain another percentage point of efficiency. Silicon MOSFETs and IGBTs have been the go-to component for power designers for decades. However, things are changing. With the introduction of wide bandgap semiconductor solutions, silicon carbide or SiC and gallium nitride or GaN are changing the way power converters are built. To understand how we move from silicon to wide bandgap alternatives and to learn what the core differences are, I'm joined by Anup Bhalla from UnitedSiC, now Qorvo, and Denis Marcon from Jiao from InnoScience. So I'm just going to bring the guys in. Here we go. Oh.
Hello.
There we are. Hi. So Anup Bhalla, welcome to the show, first of all. Could you just tell us a little bit more about UnitedSiC in a couple of words?
Yeah, UnitedSiC has been around since 1999 as a spin-out from Rutgers. Did a lot of R&D in silicon carbide in the early days, and became transitioned into a product company around 2010 in that time frame. And in the last decade, has been known for its JFET and Cascode-based products.
Okay.
Last October, UnitedSiC got acquired by Qorvo, and that's why you see UnitedSiC is now Qorvo. We are part of their infrastructure and defense products group. There's a sister company there that does some analog ICs, so forming a new kind of product group to do power.
And what's your position at UnitedSiC and your background?
I'm a dyed-in-the-wool power devices guy from the time I graduated in the mid-90s, long time. Worked on silicon for the first 15 years, low voltage, high voltage IGBTs, super junctions. And then since 2012, I've been doing silicon carbide at United Silicon Carbide. I'm the chief engineer for power devices for Qorvo.
Super, thanks very much. And now I'm going to move over to Denis from InnoScience. Maybe you could tell us a little bit of the InnoScience story.
Yeah, indeed. So, hello, everybody. So, indeed, InnoScience started, let's say, at the end of 2015. And from the very beginning, let's say, we focus on 8-inch GaN on silicon. So, we are, let's say, a newcomer in the Western world, but de facto, we are the largest IDM, the largest manufacturer of 8-inch GaN on silicon. So, whereas other people are focused on 6-inch, we are the only one, let's say, that are today mass manufacturing 8-inch GaN on silicon power devices. So last year we became international, and therefore we are giving our device to the world.
Super. And what's your role at InnoScience?
Yeah, so I'm the general manager of InnoScience Europe, taking care of the customer in Europe and making sure we're going to serve them well with GaN technology.
Smashing.
Yeah.
And Jiao, you've also joined us from InnoScience. Can you tell us what your role is and background?
Okay. My role currently in InnoScience is the senior manager for product design and definition engineering. And I came from a power supply background, and I've been working in power supply industry for several years, and also in the semiconductor industries, mainly focused on wide bandgap device. So I've been working in both silicon carbide world and also gallium nitride world.
Super. Well, thanks very much to you all. I shall be getting back to you shortly. I'm just going to share a little bit more background about the show. Now, while I have plenty of questions on SiC and GaN for my guests, this live show thrives on the questions that are troubling you. So regardless of where you are watching, you can post your questions and comments directly to us. Throughout the show, we'll do our best to get answers or guide you to resources that might help. And between the shows, you can also get in touch with me, Stuart Cording, directly via email or Twitter. So with all of that out of the way, I'd like to bring in Anup from UnitedSiC. Welcome back, Anup.
Hi.
So my first question, Power converters that I've looked at already regularly achieve 96% efficiencies, and I've heard that with SiC you might gain an extra 2%. Doesn't that mean that all that effort that you've been putting into SiC development the last 10 years has been a waste of time? What do you say to that?
Yeah, doesn't it makes it sound like it, right? I made a 1% improvement in efficiency. It was already so high. Now I think the big thing here is reducing power losses so you can make your system smaller, better, lighter, and do new things with it, right? And so when you look at it from that point of view, take a car for instance. The traction inverter in a car. If it's a 200 kilowatt inverter and you save 1%, you're talking about saving 2,000 watts.
Wow.
1% may not sound like a lot, but 2,000 watts of heat removal from a little tiny inverter that you're trying to shrink, maybe put around the motor of a car, that's a big deal, right? You can do new things. And this applies to all kinds of things, whether it's data centers or all kinds of power electronics. So maybe we start talking about how much power we save instead of how much efficiency we gain.
Yeah, exactly. I think that's a very good point. And I think to understand that, one of the things that we need to maybe first discuss is the differences between a silicon carbide MOSFET and a silicon MOSFET or an IGB device, which is obviously the devices, the power devices that you're targeting to replace. So what are the key differences there? And what are the benefits that the development engineer, the power converter engineer is gaining?
So let me see if I can share a picture that might help you guys visualize, what the differences are between these devices, and in particular also what then we make. Let's see if I can figure this out. Share screen. Okay, it's pretty nice and well organized. Yeah. Okay. Tell me if you can see the screen, and then I'll point out what we're talking about here. I think a lot of the user base understands that, at the 1200 volt node, silicon IGBTs dominate. There's a picture of a trench-based IGBT here that I'm pointing to at the left, a picture of a silicon carbide MOSFET, and then a picture of a silicon carbide trench JFET, right? And when you use the IGBT, the resistance, if we try to make a MOSFET at 1200 volt, it would have a very, very high resistance. This just comes from the fact that in silicon, because the critical field for breakdown is so low, you have to use a much thicker voltage supporting region, and you have to dope it lightly, which means its resistance tends to be high. And to cut that resistance, the technique is, you inject electrons and holes into that region so that it'll have a low resistance. But then once you do that, in every switching cycle, you've got to move the charges in and out, right? Which ends up slowing down the IGBTs. So if you wanted to switch high voltage devices very quickly or losslessly, this is where wide bandgap devices come in, because with their high critical field, like 10 times higher critical field, you can theoretically have, a 10 times thinner region to support the voltage like I'm showing here. It's called the drift layer. And then there's no need to inject carriers anymore. So you're just charging and discharging capacitances. And this allows these devices to switch much faster. So that's the whole value proposition for wide bandgap devices. And the trench JFETs, that we make are used in cascode form to kind of do the same thing. So we'll talk more about that later. But the key point I'm making is they switch a lot faster. And so we're going to get into, well, that's all good, but they also create a bunch of problems for people when they switch a lot faster. And then this other point that people get, especially the people focused on traction inverters, is that, well, then the IGBT has a knee to its conduction characteristic. You have to first turn a PN junction on before it'll carry any current at all, compared to a MOSFET, which is linear. It's like a resistor through the origin. Yeah. And so if you're operating at modest currents, which in an EV, for example, in the traction inverter, you are most of the time, many applications are like that. You don't need to waste all of this conduction voltage drop, because that's just dissipation in the power switch. But I think the main thing you'll be interested in discussing later is, well, okay, it switches fast. So how do you handle all of that fast switching? And it's kind of, this is another picture of what happens at the lower voltage node, where the main dominant device in the market today is the silicon superjunction. Then your other guest will talk about gallium nitride hemp devices, which are very fast switching wide bandgap devices. And there's trench MOSFETs and planar MOSFETs out there, made out of silicon carbide, and then our technology, right? And in a little while, I'll explain, why we chose this technology. It's fundamentally because it allows you to make the smallest silicon carbide chip for a given resistance, which then cuts its capacitance, which then allows it in a cascode to switch very, very fast, right? And so fast switching may be good for power losses, but we'll talk more about, then what challenges people face when they try to use it.
So when I'm specifying or selecting a silicon MOSFET or maybe an IGBT, I have certain sort of parasitic parameters that I have to consider. With a MOSFET, one of the things I'm going to be looking at is probably the RDS on in order to minimize the on resistance. With an IGBT, it's more I think it's the voltage drop over the collector emitter that's sort of my concern, which is an equivalent resistance almost. How do SiC MOSFETs stack up with those parasitic parameters that are so important to me with the previous silicon technology, such as also the capacitances on the inputs and outputs?
Yeah, so I think if you want to answer the question about resistances first. At this point, silicon technology is pretty amazingly good because, I have this chart here, which I use to track the breakdown voltage rating of parts and what resistance they might deliver if I had 1 centimeter square of that chip size available to me. And, this is a line that represents the theoretically best number you can achieve with basic device structures in silicon. But because silicon uses a superjunction technique, it's now well below that limit. These two stars represent silicon devices. So at the 650 volt class, they're down near 7 milliohm per centimeter square. So 1 centimeter square of chip would give you a 7 milliohm device. These yellow dots represent some of the best GaN devices. These black ones represent some of the best silicon carbide MOSFETs. You can see they're making big jumps because this is a logarithmic scale. The silicon carbide devices, MOSFETs, are down near 2, and some of our latest cascode-based technology is down near 0.7. Right, this is the generation 4 stuff that we launched a couple of years ago. And what this boils down to is that for a given targeted resistance, you can get a lot more die on a wafer with the technology that brings you the lowest resistance per unit area. Then you can use this to fit it. You can use this to fit it into smaller packages and whatnot to cut inductances, which is part of switching fast. But one fundamental thing is that once you start having small chips and reducing capacitances, all these parts get extremely fast in the way they switch. And then you have to manage those parasitics. But the fundamental reason we are doing this is that it leads to more cost-effective devices, but more importantly, fundamentally, the capability to be very fast in switching. Then you can take it and do with it what you need. Sometimes we have to just slow the devices down because of the challenges of fast switching.
Yeah.
Does that kind of answer some of your question?
Absolutely, yeah. No, that's great. And so, another sort of area of interest is obviously then to understand which applications benefit the most from silicon carbide. When we look at maybe some of the marketing material that's shared by the semiconductor industry on wide bandgap devices, we get the feeling that silicon carbide is very robust and maybe more appropriate for higher voltages, let's say above around 600, 650 volts. Whereas GaN is more suited to higher frequency switching, but maybe below 650 volts. Is that what you see in the way you advise engineers who are looking to benefit the most from SiC?
So what I'd say is that gallium nitride silicon devices are still quite popular. In fact, dominate the market. And then there is, of course, we compete with silicon carbide MOSFETs a lot more than we do with gallium nitride devices, probably because of the type of split in applications that are being served. So I thought I'd give you the perspective on the kind of applications where we definitely see a lot of uptake of our silicon carbide devices. And in most of these places, I think the dominant competitor is either a silicon device or a silicon carbide MOSFET for us these days. So, you've heard all about the automotive. So the traction inverters, onboard chargers, and DC-DC converters. This is probably the biggest segment. But the segment that's the oldest for us is just regular battery chargers for forklifts, industrial automation. There's robotic chargers in big warehouses, those kinds of applications. Including nowadays, there's some wireless charging work for big commercial vehicles. IT infrastructure just basically means telecom base station rectifiers or server power supplies. This is an emerging and growing area because that totem pole PFC topology that eliminates the input diodes is really gaining quite a lot of traction now. It took a long time, but it's getting a lot of traction, and it's used a lot in the onboard charger. That same topology. And then I think so. You've always known that silicon carbide had a role to play in the renewable space, especially in PV. But we see a lot of uptake in the energy storage sector. So one common thing you'll observe here is that everything I'm talking about, 1.5 kilowatts or so is the low end of power. Most of the stuff is, 6.6 kilowatts in OBCs, 11 kilowatt, 22 kilowatt, high kilowatt space.
Yeah.
So maybe that's the reason, why the applications are being served by these high current discrete devices. And in the future, even higher power applications served by a lot of modules. The last category is interesting, circuit protection. So we are seeing a lot of interest now with, there's so many different DC sources. There's a lot more interest now in making circuit breakers that are solid state, that don't arc. There's no arcing. And not just that, actually, even industrial breakers, normal AC breakers, there are specialized applications where being solid state may bring great benefit. So they're having technologies that give you very low on resistance in this 1200 volt class and so on is very useful because circuit breakers carrying current all the time and wasting heat. So these days we are trying to get into the sub-milliohm class in this space. So you can talk about resistances of the kind you get from two metal contacts touching each other.
Yeah.
They give you a sense. I think it's mostly we see the power area that we serve is relatively high. So maybe that's the kind of segment where you see more high current vertical silicon carbide devices. Yeah. And I think possibly a lot of the lateral GaN devices have already penetrated a lot in lower power. Definitely in your wall chargers. See them all.
So when it comes to an application, if I have an existing design that is silicon MOSFET or IGBT based, and I move that design to a SiC based solution, what am I going to see in terms of improvements? In terms of say weight, volume, efficiency? What should I be expecting to achieve?
Right, that's a really great question. If you're designing a new system and you're trying to choose between an IGBT and a wide bandgap device, you do a bottoms-up job of doing the design for these fast switching devices. You can get quite a big bang for your buck between, if it's an IGBT, between the conduction and the switching losses, right? I have I think I have somewhere down here, maybe a table of numbers I computed a long time ago for, what happens in a traction inverter if you could ideally use, I don't have it handy, but it's like a 3x reduction in losses that's possible, power losses that's possible if you use a wide bandgap device, because less switching loss, less conduction loss, right? And so that's if you do everything by the book. But typically what happens if you are just trying to upgrade an existing design, you have to deal with these very, very fast switching devices. I'm just showing a picture of how fast some of these devices switch, and so the act of managing that and managing the EMI means that depending on your constraints, you may have to give up on some of the performance benefits here. So this is where, this meeting that you're having is very pertinent. It's just to find out, let's talk about what you can really do. It depends a lot on your constraints. If you're just upgrading an existing design, doing a bottoms-up new design, what are you willing to do?
Yeah.
How much?
I was going to say that's an interesting point. So obviously over the years, if you attend any of the congresses, for example, that are looking at and investigating power converter and power inverter technologies, there's always a lot of research going on into different types of topologies for your power factor converter, for DC and AC to DC converters. If I have an existing design, does it even make sense to just replace the silicon devices with silicon carbide, or would it make more sense to really look at the topologies I'm using for each stage and maybe consider a redesign in order to really get all the benefit out?
Ideally, if time to market was not a problem for you, you would go, I would recommend you do a bottoms up design and get the full benefit out of these parts that you're buying, shrink your system, cut the cost, make it more efficient and more robust, whatever thing. You even get more voltage margin for your products and cut their failure rates in the field. All kinds of things can be done. Yeah. But that's a choice that I find in the real world doesn't actually exist for most of our users, because they have projects they need to deliver quickly, projects for which they have platform developments for the future that have more time. So it's the whole mix. We actually got started out because it's what we make is a cascoded device ultimately. And in that device, let me show you a quick little picture of what it is. Inside there's a specially designed silicon MOSFET with a 5-volt threshold that is switching this depletion mode JFET. So from the outside, you operate it like a 3-terminal device, right? So because the gate drive is ultimately, all you need is 0 to 10 volt to drive it, right? But it can be compatible with all other kinds of gate voltages that you get, whether you're driving a silicon carbide MOSFET or an IGBT. So our generation one products, many years ago, the first thing actually they did was replace IGBTs. Now, it was not easy. Even then, you had to put extremely large gate resistances and extra gate capacitances because, you're replacing a device that's far slower. But it was a thing that people did. And when that happened, they immediately got some efficiency benefit without making massive changes to their platform. But as the years have gone by, there's more and more designs that are really all focused around wide bandgap devices. So they are generally better equipped to deal with the fast switching. And, so there's a better chance of fully exploiting all the benefits that we are bringing here. Yeah. But still, you saw the packages I showed you for the kind of products that dominate the actual business as we do it today. Many of these packages are really old school silicon packages. They have a lot of parasitic inductance. Yeah. Therefore, the devices are used and switched significantly slower than they would otherwise be. Right? So this is what, it's an evolution in the design and practice in the world of power electronics. So a lot of these old packages are being used. They are now being used a lot faster than IGBTs used to be switched, but they're still the old packages. They do have a lot of inductance. So they bring, they cause a lot of overshoots and whatnot because of the inductance. And so, we, with our device structure, we often recommend small snubbers because they really help to tame under these extremely fast changes of current, how much overshoot you'll get and how you can manage all this. Yeah. So there's a lot of education required for, switch it this way. In our case, it's not so much the gate driver that's the problem because it's a cascode. It's very flexible on the gate drive side, even for DSAT protection. All of that just works like IGBTs. Right. The big thing is the cascode is it's a bit harder to control the switching. So we use this. We use these tiny surface mount snubbers that dissipate very little power, quarter watt, maximum half a watt, to manage these waveforms and get it to all work, because the devices people are still using come in highly inductive packages. Yes, it's good you're asking about these real world challenges because that's the situation. You raise a very interesting point because that's one of the challenges of the semiconductor industry. That one of the semiconductor industry challenges is not just the development of new semiconductor devices, but also the packaging that goes with it as well. There's a lot of work that goes on
to develop new types of packages, and that's not always purely an electrical task. It's also a mechanical task as well, isn't it? It needs to be you need to be able to pick and place it. You need to be able to solder it, and it also needs to survive the challenges of the environment it's going to be put in. Is this another area that you're looking at UnitedSiC to improve the package technology?
All of us device suppliers in GaN, silicon carbide, are looking at better and better packages. One of the challenges we face in deploying new packages, I think you understand very well, is looking at how the supply situation has evolved in the world. People are afraid of packages that come from only one source. They really want this to be something they can get from multiple sources. And so the evolution of packaging standards, it's unsatisfactory. It's kind of slow. There are not well-established standard packages that you can get from other people, many suppliers, in a standard footprint that would make the user base much more comfortable with jumping to new technology. You finish the design, at the end of it, you have to manufacture it. So you've got to be able to convince your company that you've picked the best component within the constraints of actually being able to get it and manufacture it.
Precisely.
But the new packages are all coming. They are somehow delayed, I think, by the lack of how long it takes, not a lack of how long it takes us to agree on standards.
Yeah. Now, I think that's always one of the biggest challenges of the electronics industry is defining and agreeing on those standards. I don't think it matters if you're trying to define a wireless protocol or a new package or a new manufacturing process. I think that's what holds us back a lot of the time. I'm just going to turn now to our audience and have a quick look to see who's online today. So a quick hello to H. Pratt. I remember the name we saw joined us last time, and Annie and Jenny as well joining us today. Don't forget, if you've got any questions, feel free to pose them to us via YouTube, on LinkedIn, and also on Twitter using the hashtag ElektorEI for Elektor Engineering Insights. I've just got one more question for you, Anup, before we take a look at GaN technology as a comparison. One of the questions I had was regarding the manufacturing process. Obviously, we're used to how silicon devices are made. We've got a nice silicon wafer as a starting point, and then we build up in layers on top of that. Are silicon carbide devices made from a silicon carbide wafer, or is the manufacturing process different to how silicon devices are manufactured?
There's a lot of similarities. You start with a single crystal silicon carbide wafer. It's just that silicon carbide wafer comes from a boule, which is just this big compared to the silicon one that is enormous. So that affects how much the starting material costs. It's much harder to create. And then then it follows the same process. You grow an epitaxial layer on it, which is the layer that supports all the voltage in this device, in a vertical current carrying device. Silicon guys, we did that in silicon, we do that in silicon carbide. It's much harder in silicon carbide because you do it, instead of at 1000 C, you got to do it at 1550 or 1600 degrees Celsius. That's above the melting point of silicon. And then it's prone to a lot more defects, and the material is much more imperfect compared to silicon. It's very good now, but it's evolved a lot, but it's still not silicon.
Yeah.
Then after that, it's got to go to the fab, and in the wafer factory, if you look at a silicon carbide wafer fab, it looks just like a silicon wafer fab for the most part. It just has a few extra tools in it to assist with the fact that you've got to implant at high temperatures, you've got to anneal those implants at a very high temperature, but overall, it looks quite a lot like a silicon line. Might have some few specialized tools at the back end of it. Ultimately, some of the process steps in silicon carbide are lower in throughput than silicon, and therefore the wafers tend to cost more for that reason. At the end of it, though, like I described to you here, I showed you a picture where the resistance that we get, out of a centimeter square of chip size, was this a chart? Yeah, is so much lower than silicon devices that we get so many more die per wafer if you're trying to target a certain resistance, that I think at this point we are able to be fairly competitive with superjunction type MOSFETs, despite the higher cost of building silicon carbide. But the factories look, the fundamental steps are rather similar. Factories that do the actual processing of the wafers look quite pretty much the same.
Super. Well, thank you very much for all those insights, Anup. Now going to go over to Denis from InnoScience. I just add you to our stream and take that out for you. So, and we'll come back to you later, Anup, with a few more questions. So, Denis, welcome to the show. Thank you for taking the time to join us.
Yes.
Now, we're just talking to Anup about SiC, and silicon carbide devices are called silicon carbide MOSFETs, which obviously relates similar back to the silicon MOSFETs we're used to. But when I look at documentation about gallium nitride, we talk about gallium nitride transistors. Is that correct?
That is correct. Actually, to be more precise, is a high electron mobility transistor. So the magic of GaN is that you have an heterojunction between argon and GaN, and you have a spontaneous formation of an electron gas, which owns, let's say, very high mobility. And all the benefit of GaN, let's say, is coming from that high electron mobility that you intrinsically have. So it's a lateral device that allow you, let's say, to switch fast, and it is a wide bandgap material, so it can handle, let's say, high voltage.
And is it, if I were able to look under a microscope and actually see it operating, does the material inside the transistor actually turn into a gas during operation, or is it just a term we use to describe the physics that's going on in there?
It's really the factor, yeah, it's not that you see a gas, let's say, but it's the fact that you have a confinement of your channel, and it's an electron gas, is exactly the channel of your device. Perhaps let me also do the trick that my colleague did. If I show you just one slide, actually I have prepared it here. So you see the magic, you can see my screen, right? Yeah, so the magic is happening here on the heterojunction between argon and GaN. And you have the spontaneous formation of the two-dimensional electron gas. That is coming from that.
Okay, so super. It's good to clarify that, because it's just obviously a very different functionality to a typical silicon-based device.
Yeah,
and it's interesting to clarify that. Yeah.
Yeah, actually, it is similar to a silicon device, because once you have your channel that is spontaneously formed, that's why naturally these devices are normally on. Then basically with your gate, you are able to deplete the channel locally here by modulating the gate and interrupt the conduction. So it just, let's say, is like a normal transistor, but the threshold normally is negative. That is why this is what we have been engineering over the years, is to have what we call normally off operation, where basically by doing some trick on the material, let's say, you're able to have a local depletion of so locally interrupt the two-dimensional electron gas, and therefore realizing normally off operation, let's say.
Okay, so we've got the gas element of GaN devices, and we've also got they're normally on, and you've made that change. What are the other differences that we would expect to see between a silicon MOSFET and a GaN transistor?
Yeah, the other small difference. So if we look in the performance, we see the capability of GaN of switching a higher frequency than silicon, and this one enable all new sort of application, or more like, let's say, increasing the power density of the converter. This is one. The other big difference with respect to silicon is the very low reverse recovery, which I show you here. Basically, GaN, since you don't have a PN junction, you don't have reverse recovery current, which is let's say causing issue in possible system in terms of power losses. So this one I would say is the difference. The other big difference that people need to get used to it is on the gate voltage swing. Normally silicon MOSFET or even silicon carbide MOSFET, you can have a gate swing up to, let's say, plus 20 volt, plus 15 volt. With GaN, normally you are limited to 6.5 volt, 7 volt. That's why there are driver made for GaN. But
Right.
other than that, let's say it's a better device, is reach fast. You just need to know how to handle it.
Super. Excellent. I'm going to bring in Jiao at this point as well to talk a little bit more deeply on the technical side.
Okay.
So in terms of the parasitic elements of GaN, we touched on it earlier with MOSFETs. Obviously, we have a gate charge on MOSFETs. There's the RDS on. What sort of elements of the GaN device datasheet am I going to be looking at, and how do I compare them with what I understand from the silicon MOSFET world that I'm trying to replace?
Okay, yeah, let me just also bring out a slide to answer these questions. Okay. Now I'm sharing this page. So basically, this is a page that compares the parasitic parameters between the silicon and the GaN. And from this left-hand side figure, I think one major difference between GaN and silicon is that, as Denis said, the GaN doesn't have a p-n junction. And as a result, there's no body diode. And the major impact for this difference is there's no reverse recovery. So the loss will be, the turn loss will be different. And also, without the reverse recovery raining, there will be a lower noise. So this is beneficial for EMI using the gallium nitride device. And also, this table gave a quick comparison of some of the major parasitic parameters between the GaN on the first, second column and the silicon on the third column. So I think it's very obvious that the gallium nitride device has much smaller parasitic parameters, such as the gate charge and input capacitance and output capacitance. And when it translate into a system level performance, a smaller gate charge and input capacitance means a faster switching speed, makes the switching energy smaller. And also the smaller junction capacitors, especially the energy or charge related junction capacitors, makes it easy to achieve the ZVS for some of the soft switching applications with a smaller loss. So this is the beneficial for both a hard switch topologies using GaN and also the soft switching topology. So I think that's the major benefit.
Yeah.
With the smaller parasitics.
One of the points that we touched on just there with Denis and also yourself is on the gate driver itself. So we're limited, I think, on the upper end of the gate voltage to 6-7 volts or so on GaN devices. And I think isn't there also a limitation on how negative you can go with the gate or the emitter? The base voltage of those devices.
Yes. I think this table also gave a comparison of the gate voltage and the driving requirements between an E-mode gallium nitride device and a silicon MOS. So we already covered that for the GaN. The maximum continuous voltage range is from around -6 volt to 7 volts due to this P-GaN gate. And for silicon, it's a little bit wider range, basically -+20 volts. So I think it can be a view into two different perspectives. On one hand, for the gallium nitride device, the turn-on voltage is much lower. You don't need to drive it up to 12 volt or 15 volt to fully turn on the channel as a silicon MOSFET does. And you just need to provide like 5 to 6 volts turn-on voltage to fully turn on the device. That will be much smaller driving loss associated with that lower voltage. And also, as for the negative voltage, basically you don't need to use a negative off voltage to turn off the gate or to turn off the device. Basically, most of the application just use 0 volt, and that will save the gate driver design complexities. You don't need to generate a bipolar gate voltage, just from 0 volt to 5 volt or 6 volt.
One of the things I heard about GaN transistors was that the reliability over time could be compromised if you're not careful with the gate drive voltage. Is that still the case today? Can I have long-term reliability issues if my gate voltage goes too negative too often?
I think we can answer this question from, again, two perspectives. So I think one perspective is that you can have a good gate drive design. That's why we have some gate driver design recommendations to climb the voltage, to be not to go to too negative. And here shows a gate driver design examples or recommendations. You have voltage dividers that climb the gate voltage during the turn on and turn off transitions. And also you have a Zener diode that climbs the voltage below the maximum rating to protect the gate. So that's one perspective. The other perspective is that because you don't need to use the negative voltage as the silicon or silicon carbide device does, basically you don't need to go too negative during the off state. You stay at zero, and the maximum negative voltage is minus 6 volt. So you have still some margins between the maximum negative voltage and your off state voltage.
Now, one of the key important discussion points around moving to these wide bandgap devices, as we were talking earlier with silicon carbide, is considering new topologies. One of the areas where GaN has seen some interest and lots of, let's say, design examples, which come up regularly in my postbox anyway, in my email account, are for mobile phone chargers. When I move to using GaN, do I also change the topology of my power factor converter and my AC-DC converter or DC-DC converter in those applications too, to really get the best out of what GaN can offer me?
Yeah, I think this is the question that people often ask. I think on one hand, definitely the wide bandgap device, especially the gallium nitride device, enables some of the topologies that is previously not possible using the silicon device. For example, the PFC circuit, for any adapters or any chargers above 65 watts, the power factor correction circuit is required. And previously with the silicon device, the dual boost or bridgeless PFC is a very common topology or a very conventional topology. Because the silicon device has a large bodied out reverse recovery charge or reverse recovery loss. Therefore, the totem pole PFC with a simpler structure cannot be used. Right. But the gallium nitride device doesn't have a reverse recovery charge. As a result, this is a new topology recently enabled by the gallium nitride device in both the adapters above 65 watts and also some other higher power applications like server PSU. So this is an example of a new topology enabled by the gallium nitride device. And also for some other chargers, I think you can still use the previous topologies, but again, also bring in some benefit like lower EMI loss, lower EMI spectrum, and also a better secondary side synchronous rectifier driving circuit.
Okay. Now, when it comes to manufacturing gallium nitride devices, are we starting with a gallium nitride wafer, or is the manufacturing process somehow different?
Yeah, let me take this up. Yeah, thank you. So actually, you could start from GaN substrate, but actually the beauty of GaN is that you can go gallium nitride on top of silicon. Now, it's not just that you grow GaN on silicon. You have a lot of engineering and buffers in between. You grow GaN, but de facto you can grow GaN on silicon. And the challenge, let's say, is the larger the wafer size, the higher the challenge. So we have been doing that, as I said, on 8-inch, which is the largest wafer size available today. The other beauty of GaN, and this is what we have been doing at IMEC, I did my PhD at IMEC, and is the fact that you can use a standard silicon process to manufacture GaN transistor. And therefore, you can take advantage of more than 40 years optimization done for the silicon manufacturing and apply directly with GaN to GaN. And this one gonna give you a spectacular throughput. And therefore, the end result is a cost-effective technology. That's it.
And how does it look at the minute with the availability of GaN devices? Obviously, we've seen a lot about the semiconductor crisis. There's endless numbers of semiconductor components like microcontrollers and A to D converters and all these sort of things being delayed, unable to deliver. Are we saying a similar situation in wide bandgap, or is the situation there a little bit more relaxed?
I think the situation is overall more relaxed. Don't want to speak for my colleague. What I can say from us is that since we control our own manufacturing, today the lead time of our GaN is around 18 weeks. So rather quickly we can provide GaN device much quickly, let's say, with respect quicker than what you can do with silicon, that is like 56 weeks. We've seen some cases I hear. So in that respect, I would say GaN is not suffering for that. Actually, we are. I see some customer that reaching us out to use GaN as don't want to say a replacement of silicon, but to change their system because they lack of silicon, and then they take advantage of the GaN properties and better system. Whereas in the past, people were coming to us to get a better system, so the motivation was different. And this is a big opportunity for people getting even more familiar with GaN.
Now, as I was speaking to Anup from UnitedSiC, I was saying that often I get the feeling that SiC MOSFETs are typically used in higher voltage, more robust, powerful, high wattage applications, high power applications. Where do GaN transistors typically get used, and what sort of application spaces should we be looking out for more GaN usage in the future?
Yeah. From my side today, indeed, is more on the 650 volt application and below. We see two domain like 650 volt and also low voltage between 30 and 150 volt. Is still relatively low power, let's say, but we are working in our portfolio to make available much device with lower iron, and therefore that they can enable higher power applications. This is what I see. Application example that I see today is the quick charger, DC-DC converter for data center, where we are talking about 300 to 600 watt. I'm also see GaN using in LiDAR and in other application. And in the future, I see GaN also penetrated in the automotive, first in the DC-DC converter, second in the OBC. And then one day, once we're going to have 1200 volt GaN device available, then I think that we could even start targeting more higher power application and perhaps even the powertrain. Of course, silicon carbide, they have a time advantage. They are already in that market. So it's going to take a little bit of time to use GaN in the higher power application. I don't know, Yang, if you want to add anything to what I said?
No, I think you basically covered everything. I think, yeah, as you said, the adapter is still the major focus target, but more and more, I think we'll go into a higher power, starting from the server power, and then automotive, and eventually maybe renewable energy and energy storage systems.
Okay, I'm just going to bring in then Anup into the discussion, so we can have a bit of a broader discussion about wide bandgap. My first question is actually to, I guess, from InnoScience. Are you also seeing the same challenges with packaging for GaN power devices?
Yeah, what I would say that I do see the request of the customer to try to have pin-to-pin compatibility, dual source, and etc. That's something that is highly appreciated by the customer, I would say. And what I will see is that we need to. So today we are using actually standard packaging like DFN because customer, they are familiar with that. So we try to ease the adoption of GaN. So we're gonna try also to leverage in the future double cool DFN or other packages that is going to allow us to get the better thermal dissipation. This is what I can say.
Yeah. And one of the big things coming up in the industry here in Europe, it's a very important event, is obviously the PCIM Europe. It's a trade show where everything to do with power conversion, green energy, green transportation is covered. I think both of you are exhibiting at that show. Denis, where is your stand going to be at the show?
Yeah, our stand will be in the Hall 7 in the booth 249. So we're really looking forward to see everybody in person. And we're going to have several demo from DC-DC converter, AC-DC power adapter. We have also exciting, let's say, results from the project we have with Center of Excellence. So we are really looking forward to meet customers, meet partners, and show and discuss what they can do with GaN and how they can take advantage of GaN today.
Sounds good. And Anup, to you as well, have you got a stand at PCIM Europe?
Yep, Hall 7, I believe, booth 406.
That's
I'm
correct.
Just looking at this information here.
I checked as well.
Yep. And then we'll do what Denis is doing and have the high power type demos that I've been talking about.
And just on that discussion of demos, if I'm a power engineer looking to get started with silicon carbide, what sort of evaluation kits or demo boards do you have available where I can maybe get started without having to maybe get to into an application that's very, very high current or high voltage? Do you have some easy to use low voltage demonstrators or eval boards?
I'll go first. I think
yes, please. Yeah.
There's a range of demonstration circuitry and information available. I think most people would typically start with a simple double pulse demo board for single or many parallel devices. In our case, paralleling is a big thing for high power. So they just get those and use it to understand the basic switching characteristics in a well-defined environment. Right? Reproduce what we have in the lab, get the same sorts of waveforms, gain some confidence, and move on from there. Being said that, at this point, we've been in the market long enough that I have to admit that some of our most sophisticated customers are probably better at doing this stuff than even we are. It's good to be at that point that some of the engineers at these top companies, they're very good at handling all of this stuff.
Yeah, I think we all have to admit there's a lot of creativity out there, isn't there?
There really is. Yeah. Please go ahead, Denis.
And Denis and Yang, what's it look on your side for trying out GaN?
Yeah, we have also a set of demo board that customer can take, especially a lot on the quick charger, but also LED driver, DC-DC converter. We also have a double pulse evaluation board, as Anup said. And but as Anup said, there are a lot of customers that they know what they want and they know how to use it already. And that is, of course, is a very good customer because you don't have to educate them and etc. But we are there to serve and to help anybody that wants to get familiar with GaN and start using it. And we have a very strong team to support this, like the team of Yang, for instance, that can do that.
Yeah. Let me just add one more comment. We also have many of the application notes and documentations on our website, like the gate driver recommendations and also how to parallel devices. So those kind of white papers and documentation is another supplemental materials for the customers or users to understand.
That's a great piece of advice. Thanks very much for that.
And
also,
can I just interject one other thing? And those basic tools for learning the devices and switching them, some basic application circuits for totem pole, all that stuff. You need to provide that as a supplier. But we've got a tool now on our website called the FetChat Calculator. It's a really easy to use tool where you select your topology, put in your inputs and your thermal constraints, and it just tells you. You can select devices and then it's just going to tell you how hot the device is going to get, how much power it's going to dissipate in the conduction and switching state. So it's a very quick selector for what's going to work and not going to work. Right? It's not a simulator. It just does all the calculations in the background. So you can narrow down and not waste your time with a lot of different parts.
That's an interesting point as well that you mentioned with simulation. Anup, are you seeing that power designers are increasingly turning to simulation tools in order to, and sort of like these Monte Carlo type assessments or simulations of circuits in order to figure out really where to squeeze out that last half a percentage point of efficiency?
Yeah, I mean, there's a range of, it just depends on the customer type you're working with. I do see, the very sophisticated use of simulations now to find the most optimum design. Definitely, some people do that. Many cases are not like that, though. They're in a practical hurry to get something done
Yes.
and released.
Right.
So in that situation, this other thing I'm talking about is more useful. How can we quickly help you narrow down to the few things
Okay.
that work, and then quickly help you get that evaluated so you can get on with it, right? And have a solution of the kind where you already have a reasonable understanding that when you switch this fast, how much EMI you're going to get in the gigahertz spectrum and what's going to happen. So you have a chance of an actual design win success. This is what is most of what goes on.
Okay. Yeah. And Denis, Yang, do you also have some software tools available to complement the application notes and boards?
Actually, I think we also have some of our internal tools to calculate and simulate, and also we provide a SPICE model for our device for any customers want to do some system level simulations.
So that means that I can use sort of standard SPICE circuit simulations just as I would do for a silicon-based switching technology.
Because I think SPICE model is more common platform for simulations.
We have available in several other platforms as well, in case customer is not using SPICE, let's say. So, but I do share with Anup the same feeling that indeed we can provide model, people can model, can do things, but there is often the urgency of making it, let's say. So, yes. Yeah.
Super. Okay, well, thank you very much, everybody, for your time. I'm just going to say thank you to Anup from UnitedSiC for your inputs today, and again from Denis and Yang also to sharing us all those insights regarding gallium nitride switches. I'm just going to remove you from my system, say thanks very much, and just turn back to our audience and provide you with a little bit of an outro to what we've learned today. So, having spoken to our guests, it seems clear that if you're sick of IGBTs or you're looking for a performance GaN over silicon MOSFETs, apologies for the joke, you should be taking a look at wide bandgap devices. Many thanks to today's guests. That's Anup Bhalla from UnitedSiC, now Qorvo, and Denis Marcon and Yang Jiao from InnoScience. You've delivered some brilliant insights for us today. If you are hoping to visit the world's premier power exhibition, PCIM Europe in Nuremberg next week, but you're unable to attend, there's no need to worry. I shall be going on the 10th of May to explore all the latest technologies and solutions for you on the trade show floor. So keep an eye out on the Elektor TV channel and on YouTube for my insights. And if you want to see what else we've planned, you can also drop by the Elektor Engineering Insights page at elektormagazine.com/elektor-engineering-insights. So that wraps it up for today. Please like, subscribe and share wherever you're watching. And don't forget, if you'd like to join me as a guest, write me an email, drop me a tweet or reach out to me, Stuart Cording, on LinkedIn. Thanks for joining us today. Stay in touch and don't forget to keep asking your engineering questions.